So thanks for the organizers for giving me the hard task of wrapping up the session and completing everything that is missing in between. So I will try to put together natural observations, experiments, and models. I will be focusing only on ductile strain localization, and I will be focusing also on the connections between scales. So let's start simple. What does the observation of nature tell us is that ductile strain localization occurs at all scales, from the centimeter to hundreds of meters, and that it results from the spatial heterogeneity in the mechanical behavior, so lateral variations in rheology. A last point that we should not forget is that both weak and strong heterogeneities are important. We should not focus only on strain softening processes. What we see when we look at experiments is that most experiments don't show any strain localization at the sample scale. Why that? Because most of them use monomineralic aggregates, so quite as homogeneous as possible aggregates. But even when you are working on biphasic aggregates with high strength contrast, like the torsion on halite and calcite at the concentrate height that we see here, we have a rather homogeneous deformation at the sample scale. Why that? Because the soft phase that is halite here accommodates most of the strain. The picture changes when you look at constant stress experiments. This is what Miki was talking about later. And in this kind of experiments, we see a weak strain localization. Here is pure iron-rich olivine that is marked by this anastomosed foliation that is composed of small variations in grain size and crystal orientations. And this difference between constant strain rate and constant stress is something that's predicted by theory that shows that the growth of instabilities is favored at constant stress boundary conditions. So this points that we should look further at this kind of experiments, even if they are hard to do. And we should also think about which are the actual boundary conditions in nature in our models around the shear zone. Where do we really see strain localization in experiments? Is essentially when we are working with polyphase aggregates that have a moderate strength contrast. In this case, we have this enhanced deformation and interconnection of the softer phases that produce a very strong strain localization, as you can see here in this experiments on gneiss, but we can also see here the shear zones that form on the calcite with anhydrite torsion experiments here. And you have also an isotropic weakening because you are forming continuous layers parallel to the shear plane of the soft material. So it softens a lot if you continue shearing, but if you try to deform in another direction, the material is not necessarily softer than it was before. Sorry. So if you go back to the first statement that strain localization results from spatial heterogeneity in the mechanical behavior, we have two types of heterogeneity. It can be pre-existing and it can be inherent of the material, like the variations in strength inside a granite because you have minerals with different strengths. But it can also be formed by previous processes that affect the plate, like the lithological variations we see in any geological map of a continental plate. But we can also see in the plate pre-existing structures that reproduce heterogeneity in anisotropy that will also produce strain localization. And at the plate scales, as you can see here, when you are looking at seismic tomography, we can have lateral variations in the geotherm that can also produce the superposition of strong and soft blocks inside the plate. Can we model that? If Thibault had shown his own presentation, we would have seen that we know quite well how to model meso and regional scale heterogeneities. So what is here on the right side is one of the pioneering works to model the effect of heterogeneities in the plate deformation. So they were studying the role of the stiff tarrying craton in the strain distribution associated with the India-Asia collision. And you can see that you have a very strong and well-developed shear zones that develop at the boundaries of the stiff blocks. So this was one of the points why we should not forget the stiff heterogeneities. This is a more recent work by Thibault, where he looked at the effect of a rheological layering in a continental plate on the strain distribution and strain localization during continental breakup and extension of the plate. When you look at the microscale heterogeneities, it's much harder. They are always present. There is no homogeneous rock, even if it is a monomineralic rock. The fact that the grains have different orientation, it produces heterogeneity inside the rock. The problem is that these heterogeneities are much, much smaller than the mesh size in any geodynamic model, and they evolve with strain. If we go any farther and look at the rheological heterogeneity that may be created by the deformation itself, so you have processes that are very well studied, like shear heating. We can also produce strain localization because you have interactions between the brittle and the ductile deformation by producing stress concentrations at the fold tips that produce strain localization in the ductile crust underlying these folds. And then you have all the strain localization that is associated with the evolution of the microstructure by itself. So you have the grain size reduction that Miki talked quite a lot. We can also have fluid or melt focusing in the shear zones. We have quite lots of evidence in nature for this kind of process. We can also have reactions that are triggered or favored by the deformation that produce soft phases. And we have the evolution of the microstructure in a multi-phase aggregate that produce compositional layering and that produce a very, very strong anisotropic softening of the material. Like the previous slide, we know how to model shear heating quite well, and there are a large number of papers on that. We also know how to model the interactions between the brittle and ductile deformation, although it's much harder because we are working in very different time scales and we have a poor knowledge of the transient rheologies. But when we start to look at this evolution of the microstructure, it gets harder because here too, we are producing rheological heterogeneity and anisotropy at scales that are much, much smaller than the mesh size. When you look at the field, these grain size reduction zones are always tiny zones intercalated with zones where there's no grain size reduction. So we have a lot of variation in grain size in the rocks. So this comes to what, for me, is the major problem we have now in modeling strain localization. That is the scale transfer problem. Most processes producing rheological heterogeneity during deformation occur at the millimeter to centimeter scales. So the first question we have to ask ourselves is, are these processes the ones responsible for large-scale strain localization? And when I'm talking about large-scale strain localization, I'm thinking about shear zones that are tens of kilometers wide, or what makes plate boundaries weaker than plate interiors, okay? Or even the process that can produce the creation of a new plate boundary inside a pre-existing plate. If these processes are really the ones that are important, we really have to work on figuring out how to model these processes that will be always at scale lower than the mesh scales in our geodynamic model correctly. The other question is that, as you have seen, they are formed and they evolve with progressing deformation. So you have to be able to define evolution's law that describe this evolution correctly. Modeling imbricated spatial scales is not something that is an exclusivity of geodynamics. It's something that appeared to everyone that wants to model a natural system. And it comes out because you have a large series of processes that occur at different scales and which are governed by different physical laws, okay? So the problem is that we have to, when you are doing a modeling, we have to discretize the system. At that one time, we have a mesh size where we have to truncate our equation developments. How can you go farther? You can use multi-scale models where you take a very precise physical model of a small scale process and you incorporate it inside the large scale models. We do that, for instance, when you are modeling mechanical anisotropy. We incorporate crystal plasticity models at the rock scale into each element of the geodynamical codes. This is efficient, but computationally very costly. If you want to get fast, what you do is replace the small scale processes by a parameterization. It's a simplification, of course, and the approximation will be at best as good as our knowledge of the process. If we increase the computational power, we can push the boundaries towards smaller scales and allow the simulation of a larger number of processes. But the system we want to model is so complicated that it will not completely solve the problem. So, sorry. The other thing that you have to deal with is that even we know how to model this process, and we also have seen that they produce variations of physical properties at much smaller scales than the meshes. How to deal with this? We have usually two approaches that are used. We have the homogenization approach, where we average the properties, or you have a weak chain approach, where you consider that the weakest element controls the bulk behavior. In most cases in geodynamics, we are working with homogenization, and what we are doing here is taking a material that is heterogeneous and representing it by the average of the mechanical properties of the material. The one we can get, for instance, if you do a deformation experiment, you only look at the bulk curves. The problem in this case is that you get a homogeneous hardness all over our finite element model and no strain localization at all. Is there any other possible way of dealing with this problem? Yes, there are stochastic models in which you describe the variability of the properties and randomly sample it in the models. It's something that's not new. It has been currently used in recent years in weather and climate modeling. And these models produce more reliable forecasts in these disciplines because they quantify the probability for a different phenomena to occur for a given uncertainty range in the physical parameters. So we start to work with probabilistic predictions. We know the uncertainty and we give probabilities to have a result instead of getting a single result. This is what we propose to do. So it's something that we'll be trying the next years for the geodynamics, and something that we propose to do in a project called Re-Evolution that has just been funded by the European Research Council. And what we'll do is use a stochastic description of the rheology. Let's just talk about the hardness, how easy it is to deform a rock, of course. And then we will describe these variations in hardness by a probability distribution function that gives the whole range of responses you can get inside the material. And we randomly sample this distribution function to give a hardness in the different elements of our finite element model. This will give rise to heterogeneous strain rates and stress fields. And because the stress and strain rate change from point to point in the model, the evolution of the hardness will be also changed. So each point will have different probability distribution functions in the next step. And what we hypothesize is that by coupling between variations in the hardness and variations in the stress strain field, we can get strain localization. Thus, it is completely idealistic. This is just a simple proof of concept we have done. And it's a very, very simple model. You have pure shear, okay, compressing from both sides, applied to a plate that's composed by 100% of olivine with a constant temperature. And we model this olivine plate is deforming by dislocation creep, and we are simulating it using a stochastic formulation of the Goury et al. Flow law, where you have both a power and an exponential component. It means that you can model both the high and low temperature dislocation creep of olivine. So if you use the traditional deterministic simulations, this rheological parameter here is a constant, and you have constant strain rate and constant stress. If you just randomly find this parameter, you get essentially noise. But if you start to consider that you have time and space correlations in the process, we start to have organization of the strain rate with formation of strain localization zones and of the stress field. So it's clear that it's not putting stochastic developments in the rheological models is not sufficient. We have also to be able to describe correctly the processes for which we are using this kind of approach. To do that, we also try to look in more detail to the feedbacks between the evolution of the microstructure and strain localization. And these are experiments on ice with in-situ follow-up of the evolution of the strain field that were performed by Thomas Chauve during his PhD in Grenoble under the supervision of Maureen Montagnat. So what you have here is the initial microstructure. What you have here is the final microstructure, and you can see very well the dynamic crystallization and grain size reduction that you have in the sample. And these are different snapshots of the strain field during the experiment. You can see that from the beginning, before anything starts, you have strain localization because you have grains with different orientations. So you have different strengths of the grains and strong strain compatibility between them. This triggers dynamic crystallization. So you see that you start to have noise here. It's related to strain localization you see here. Strain localization and the strain concentrations move around the rock. But the final result is that you have much less strain localization in the end than you had in the beginning. So what you are seeing here is something that's completely unexpected. You're seeing grain size reduction by dynamic crystallization that is producing strain delocalization. And why we see that here? Because recrystallization reduces the strain incompatibility between grains, and by doing that, it reduces the stress heterogeneity. This is just another picture of another set of experiments where you can even see even better this delocalization, okay? And you see that the very pixelized image here is because you have lots of strain dynamic crystallization in the end of the experiment. And so it really says that you have to go back and see how robust are our beliefs we have between the relations between the evolution of the microstructure and strain localization. And in the evolution, we will do that by doing much more experiments on both ice and magnesium alloy, and we will be coupling these experiments to measure scale models where you try to implement directly the stochastic descriptions of rheology and its evolution. And to conclude, just a few points that my idea is that there should be food for the discussion that will start. First, ductile strain localization is a direct consequence of the evolution of the rheological heterogeneity in the system. And in most cases, once it starts, it changes it. So you have to be able to know the feedbacks between the two if you want to model it correctly. This heterogeneity exists in nature at all scales, but it's often stronger at low temperatures. The nicest observations we have of strain localizations are in low temperature shear zones. Most processes producing rheological heterogeneity during the formation occur at the millimeter and centimeter scale. And here I have a first question to ask ourselves, are these processes the ones that are really important? I don't have a final answer for this question. But if yes, we really have to be able to simulate correctly, first, the effect of the submesh scale processes on the large scale strain localization, strain and stress distributions. But we also have to be able to simulate the effect of the large scale fields on the evolution of the small scale processes. Another question we have to ask ourselves is how robust is our knowledge of how different physical processes change material properties and of their effects on the stress strain fields. But this question comes from the in-situ observation of ice deformation that I just showed, where the process that most often is proposed to be the one controlling the strain localization is just producing strain delocalization at the scale we are doing the observations. And the last question that could be also interesting for both natural observations and models is which are the actual boundary conditions around the shear zone in nature in the experiments, because we have seen that the behavior of the system is completely different in constant stress or constant strain rate boundary conditions. And probably in nature and in the models, it's neither one or the other. It's something in between. Thanks very much for your attention.